Okay, now let's start. We're on quantum computing part 2. We're talking about gates today. Last time. Oh, let's write the title here. Look at, we're going lowercase too. Quantum computing part 2. Now, quantum computing part 2. We're going to be so as always, I'm going to start with the last time, and then we'll get up to date on where we were. So if you are just joining us for the first time, this is a little bit of an outline of what we did last time. Last time, we discussed what a qubit was, right? A state of some kind. We had a couple. They're analogous to the computational bits, 0 and 1, except for ours, like I said, we use states, where we have a 0 state is in vector notation, because we can establish the state vectors, right? In vector notation, it is 1, 0, and in the state 1 in vector notation is 0, 1. And these are just ideas. This, like I said, this is just a state. A state is a vector space, or a state is a vector inside of a vector space. And this is just the vector space that we choose to use for a basis. But it can change, and we'll talk more about that at the end of today. Okay, so what else do we talk about? You can talk about the individual states as qubits, 0 and 1, or you could talk as a superposition of the basis states. So you could have a qubit that looks sort of like this, where it's alpha 0 plus beta 1, where it's a superposition of these two states on 1. And today we'll see different ways of combining the states using gates to get stuff like this in the end, vice versa. And we also talked about how you can have multiple qubits considering tensor products of single qubits. So you might think that you could have a state, again, where you might have 2 qubits, which have different, could have the property of being in some superposition of many states. So we might think you might have some prefactor, some probability amplitude, alpha 1, 0, and 1, 0, and then plus alpha 1, 1, and 1, 1. Okay, so you might have some superposition of states. Can you guys see that? Is that too small? I'll have to make sure I write larger for the future. But that is alpha 1, 1, and then the state is 1, 1. Okay? And then we also discussed measuring 1 qubit and how that can transform the state, right? So the idea is we're going to talk about gates today. And there's I don't know if I want to split up and to say that there's necessarily two types of gates, but there is a large distinction between measuring and having a measurement gate and having a Bill, I don't see. Oh, I see Bill. And a measurement gate where we take a measurement of a qubit and having a gate that's used in the circuit. Those are two very different things. And we're going to talk. That's the kind of the focus on today is what a gate is, a quantum gate. But that's not to be confused with the measurement gate. What we did talk about last time is how you're able to take a measurement of one of these qubits. So the example that we used was, suppose we measured the first qubit and found that the first qubit was 0. Then this is going to transform the state, psi, prime now, because it's a new state, into a superposition of 0, 0, of alpha 0, 0, 0, 0, plus alpha 0, 1, 0, 1. And then we also emphasized the fact that we didn't emphasize down here because we just assumed it was going to be kept inside of these alphas. But now it's a little different. Now we're going to assume that it's not inside the alphas because of our originally using it inside the alphas. And what this means is we can have a normalization factor. And we also, this was still last week, this is still a review, where we talked about making sure that the probabilities of it adds up to 1. Right? When we did, probabilities add up to 1, or 100%, right? You don't want a probability where it's going to be either less than 1 or more than 1. So we called it normalization. So in this scheme, we can just assume that the normalization is inside the constants. But now that we have measured a qubit and we have gotten a 0, the only two options remain is to have the first qubit be 0. But having the first qubit be 0 means that we are going to have to normalize the front of it to make sure that we don't end up with weird probabilities. Okay, give me just a second. I gotta put my hoodie on. Hold on. All right, there we go. Sorry about that. What do you think science in years to come? Bryce, I'd love to answer that, but that's kind of a big question. We can talk about that after this. I would love to talk about that after this if you're cool with that. That's a great question. And I'd love to talk about that for sure. I think the people in chat would have some great ideas about what they think the years are going to come, or what the years are going to bring it for science. Definitely. So let's do that at the end. Definitely. I think that's a great conversation. But for now, let's finish. Let's keep working on this. So this is just the last time still. But we have a lot to unpack with this last time. So yeah. So we can have a new state. It's psi prime, and it has a superposition now of the zeros 1 and 0, or 0, 0 and 0, 1 state, because like I said, we have measured the first state as 0, 0. Now, let's start for today's stuff. So we're talking about gates. And it's no surprise that classical computation requires gates, right? Classical computation requires gates, logical gates, and wires. So the wires, they just carry the information, and the logic gates, they can change the information or adjust the information based off of what you need accomplished by that classical computer. So let's do this. Quantum gates. So it's no weird thing to think that there's a classical version of this stuff that does the same thing, right? So for instance, let's talk about a single bit logic gate called the NOT gate. Now this is classical again. So maybe we should specify here, classical NOT gate. And the NOT gate is a single bit gate, and what that will do is it will just interchange the value of your input. So for example, if you have a 0, it'll take the 0 bit and turn it into a 1 bit. If you have a 1 bit, it'll turn it into a 0 bit. And that's the point of the NOT gate, right? Well, it's not too hard to imagine that there's a quantum version of the NOT gate, right? And that quantum NOT gate is going to have a very similar property. Namely, if you're going to have a 0, it'll turn it into a 1. And if you have I guess we should write that down, turn it into a 1 bit, and qubit. And if you have a 1 qubit, it will turn it into a 0 qubit. So if we took the state alpha, so our normal state, alpha times 0 plus beta times 1, this would then become, after we apply the NOT gate, it would then become alpha 1 plus beta 0. And we're basically switching the gates as we applied the quantum gate to them. Now, there's some more formalism to this. We can actually look and see what this looks like as a matrix, right? As I said before, these are vectors. So we should be able to think about gates as operators, right?
Did you dehydrate?
I did dehydrate multiple times. Sunless night, like your name. Thank you for the follow. Welcome, welcome. So we can talk about matrix form of these quantum gates. So the NOT gate traditionally has letter X, capital X. And this has the 0, 1, 1, 0. Why this matrix specifically? Well, this matrix specifically does the exact thing that we want it to do, right? So if we were to take our state, okay, our state psi as alpha times 0 plus beta times 1. Now remember I had the vectors up there before where the 0 vector was 1, 0. The 1 qubit was 0, 1. Then if we take our psi, we can write that as a vector form, right? That will take the shape of alpha and beta, right? Like that. And then we will have, so if we want to apply our operator, x to psi, that's the same thing as writing out in matrix notation 0, 1, 1, 0 times our alpha beta. Now let's do this calculation to find out what's there. This is the Pauli matrix. This is the X matrix. Oh, I see what you're saying. Yes, that's probably, I gotcha. So the sigma X. I always think of the first Pauli matrix as Z. But yes, this is the X Pauli matrix. You're right. Okay. And if we do some matrix multiplication, we'll take this vector, we'll multiply it by the top here, and we'll get beta. And then we'll multiply it by the bottom, and we'll get alpha. And that's, now you can see, is the mic rubbing? I put the hoodie on to prevent the mic from rubbing. Oh, I wonder if the hood was rubbing. Okay. Okay, so alpha, multiply like this so that it's just beta, alpha times 0 and beta times 1. So we add those two together, we get beta. And then if we take this vector, multiply by the bottom of the matrix, we get alpha times 1, beta times 0. Add those two together, we get alpha.
We learned nothing from the builds.
And we get exactly as we want, a swap in the system, okay? Now, I also can't hear it because the music is so loud in my ear. So I can't hear the microphone too well. Circuit 007, welcome to the channel. Thank you for the follow. All right, so this X does accomplish exactly what we want, right? It is, in fact, the gate that will switch our states. So that's cool. So now let's see, we have, let's talk about a condition that's very necessary for gates, and that is the condition of unitarity, right? The gate must be normalized. If we take some psi to some psi prime, the idea is that it still must remain normalized, okay? Because again, like you can't apply a transformation to it, or apply a gate, excuse me, you can't apply a gate to it, and then all of a sudden get different probabilities in the end. Or I should say, you will definitely get different probabilities, but the probabilities should always still add up to 1, okay? You do not want to have a gate that will have probabilities that add up to like 2. That doesn't make sense mathematically. So the idea is we need to have a unitary gate for every, our gate needs to be unitary. That's what I meant to say. So now let's discuss what unitary is. So if we have some gate U, then the idea is that we'll always end up getting, if we take the adjoint and multiply it by itself, we'll get the identity matrix. That's the idea of being unitary. Being unitary preserves the normalization such that, remember last time we had to make sure that the complex conjugate of alpha squared plus the complex conjugate of beta squared equals 1. Obviously, for this, we're just getting the same thing in a different order, so it's still going to work. So X should be clearly unitary by the fact that that works. But we could just do it really quick if you guys would like to see. So what if we have, oh, and let me remind you what the adjoint is. The adjoint is the the unitary universal church.
Explain it with entropy.
Yes.
Technically, that's just orthogonality. There's more to being unitary.
There is? In a mathematical sense or in a physics sense? Did physicists, is this one of the words that physicists have adapted and crushed? Because so is the adjoint. For all intents and purposes, physicists just use the adjoint as the transpose conjugate, which means you take the transpose of the matrix, which is switching all of the elements, all of the indices of the elements. So for example, if you have this as a 0, if this is like a 0, 1, and 0, 1, so this is element 0, 0, and this is element 0, 1, so the 1s and 0s will swap, the diagonals will swap, the opposite diagonals will swap, and then that's the transpose, and then the conjugate is just taking every imaginary number and flipping the sign, okay? So that's what the adjoint means in physics. I know that the adjoint means something very different in mathematics, something about cofactor matrices or something like that. I don't know, something I don't know. But if we do this, let's actually do this really quick, because it's worthwhile to see. So if we wanted to do this calculation in matrix form, it would look something like, well, if we're going to switch the diagonal terms, it's still going to be 1 and 1. That's not anything. And there's no imaginary numbers in there, so there's nothing to complex conjugate. And then it's just the same thing. And let's do this calculation really quick. 0, 1 times the top. So we'll get 0 and 1. Add those together, you get 1. Do this, you get 1 times 0 and 1 times 0, which is 0, 0. And then you do this down here, you get 0, 0. Do this here, you get 1. And we get the identity matrix. Boop, boop. So that works. That's good. Okay, so let's keep going. And then, so this is a state. This means it's unitary, which is good. Like I said, it is a requirement that single qubit gates are unitary, okay? Except there is one exception for that, and that is the measurement gate. We do talk about measurements as gate, usually, especially when we start drawing circuit diagrams, but that is not the same thing. They are not, in fact, they are, in fact, by definition, non-unitary, because you will not be able to gather the information from a single measurement gate. You need, you is right. Nice. Yeah, you won't be able to recover the information from a single measurement gate. If you want the information about alpha and beta, for instance, you need to measure an infinite amount of measurements. Or you need to take the data on an infinite amount of measurements. Okay, where are we at in the notes? I kind of went off from the notes a little bit. So unitary is the only constraint on quantum gates, but it does get hairy because we do call measurement gates gates, but they are, like I said, different by, of course, in nature. Now, let's talk about two other main gates. One being a Z gate, which, as you can imagine, is in fact the other Pauli matrix, the Z matrix. And what does it do? What's the purpose of it? Well, the purpose of it is to take, the state 0 to itself, right? And, of course, 1, it will take to the negative 1. Oops. Stop that. Right? So that's the purpose of the Z gate. Again, we are just defining the gates. And then the reason we might implement a gate is because of a certain goal. Like we might have a certain goal to get at the end measurement. And the idea is to use the gates to manipulate the qubits to get the end goal. Okay? Now, let's do the next one. Look at that. We're already halfway done. We're cruising. The next one's a Hadamard gate. So that's going to be H defined by this 1 over the square root of 2 times 1, 1, 1 minus 1. Okay, so the Hadamard gate does something a little bit different. The Hadamard gate will take a single qubit, like 0, and put it into a superposition of the two states.
Leave me out of this.
What? I'm sorry. What? So for the 0 state, it takes it to a superposition of 0 and 1. Notice how we continue to keep this 1 over root 2. Why? What's the point of the 1 over root 2? Someone answer. Y'all's quiet today, so someone answer. What's the point of the 1 over the root 2? It's not like I didn't talk about it a bunch already. I already talked about it a bunch. The next one is 0 minus 1. That's a different setup, but obviously. Normalization, very good. That's the point, is normalization. So we always want to make sure that these, you can't start with a 1 here Obviously, if we were to measure this as just a 0 gate, we get a 1, so it's 100% going to be 1. That, that's just, in a quantum circuit, that's just that, right? But then, if we want to apply the Hadamard gate to it, our ending is going to be this, but the probability can't be more than 1. That doesn't make sense. BPRSM, thank you for the follow. Welcome to the channel. If anybody is in chat for the first time, after this we'll do some more Q&A, so you can write !ask and your question. It will go to a separate screen that I have open that I can manage, and I will we'll answer the questions afterwards, okay? All right, so, I'll try, at least. Yikes. There's an interesting thing about this Hadamard gate. Sometimes it's called the square root of not gate, but I don't know why. And in fact, the authors, Nielsen and Chang, those are the authors of the book we're following, they make specific interest that this has a unique property. Namely, if you square it, you don't get the not gate. You actually get identity. Not the identity adjoint. That doesn't even, that's just silly. But the identity itself, which I think is an interesting note to have. And it is unitary. We could go ahead and do the calculation if you want, but I think it'd be good if you want to do it. You can do it yourself, or we can do it at the end if anyone's actually interested in seeing it. The square root of not is a different gate. I know, but Nielsen and Chang say very specifically that the Hadamard gate is called the square root of not gate. And I don't know why, but I thought I would say it because they know more than I do. This gate, and it literally says, this gate, page 19 of Nielsen and Chang, this gate is sometimes described as being like a square root of not gate, in that it turns a 0 into a, that, and halfway between 0 and 1, and likewise for the 1, right? I don't know why, but they say it, and I think it's worthwhile to say. I also thought it was cool that if you just square it, you get the, if you just square it, you get the identity, which is nice because it's unitary as well, right? It has to be unitary. Lots of interesting properties with the Hadamard gate, including one that we'll use at the very end. But before we do that, I do want to make one note. If we get as far as chapter 4, there's a cool thing that happens. There's this cool thing of way of expressing this. I'm not going to write down the mathematics for it. Maybe they're saying people incorrectly say it in the literature. Oh, maybe. There is a square root of not gate, though. Interesting. Yeah, that's probably true, Justin. As I rip my microphone off my shirt for some reason. I should just get the ShamWow microphone. Okay. Now, I do want to just say briefly that, and if you do have Nielsen and Chang, it's actually in there. They actually write the mathematics, but they say they'll talk about it later in the book. So hopefully we'll get to that at some point. But there is one way of saying where, remember how we talked about the block sphere last time?
Writing the map again.
Oh, shush. No, because it's not helpful, and I don't want to write math that's not helpful right now. But remember the block sphere, right? The block sphere is the thing that we use to re-describe the state function as rotations on a unit sphere in 3 dimensions. And there's basically a way that you could rewrite all of the gates as just of different combinations of a rotation gate and a Z gate that looks a little bit differently. But like I said, we won't talk too much about that. I'm not going to write the mathematics. We'll talk about that if we get to it in chapter 4. But I don't know if we'll get that far. We might hop, skip, and jump around a little bit too. But it's more important to talk about multiple qubits, of course, right? Because then we can have multiple qubit gates. Now, they also
Math is always helpful. How dare you?
No, it's not. Justin, please tell him. The math is usually, I would say, not helpful. Actually, Justin will probably take your side. I get confused about the math, especially if it's not something that, like, they don't have it worked out, and I could do all the intermediate steps and stuff, but it just, like I said, it does seem like it's not helpful. So instead, let's talk about multiple qubit gates. The prototypical multi-qubit quantum logic gate is the controlled NOT gate. Now, we did talk a lot beforehand about multiple bit gates.
Sections you are reading on Discord.
I can. I think so. I can, yeah. The controlled NOT gate is different. Oh, geez. Rubbing. It's going to be a 2-qubit gate for our all intents and purposes. I'm not going to talk too much about the multiple bit gates, other than the one property that we need to establish. But it's very similar, and they draw a bunch of analogies and things like that that I don't really follow too well because I don't know a lot about quantum computing. But instead, or regular classical computing, I should say, or Boolean logic, as Tropical let me know. But I can describe the picture. And this is, they say this is a lot like the, I think the, what is it, the X AND gate or the X NOT gate? So the C NOT gate, or the controlled NOT gate, is what we're talking about here. And it's very similar to the XOR gate. That's right. It does exactly what they say it does exactly what the XOR gate does, except it has a couple different properties which we'll talk about pretty in depth. But the idea behind the controlled NOT gate is we want to take the state 0, 0 to 0, 0. Okay? We want to take the state, and remember these are 2 qubits now, multiple qubits. So now we want to take the state 0, 1 to 0, 1. But now, what if we have a 1, 0 in the front? So if we measure a 1, we'll actually want to change the second qubit. So the output for this is going to be 1, 1. And we could also do 1, 1. So then it's going to change the output of the second qubit to 1, 0. So that's the controlled NOT gate. Does it exist as a matrix? Okay, so this is what we want to do with the gate. And then we can write, of course, the matrix formulation of it. And it's going to have some interesting, it's going to have an interesting look to it. Namely that the idea behind this gate is that you're going to have the top square, like right here, it's going to look like the identity, whereas this one's going to look like the NOT gate, okay? So the idea is gate, or qubit A hits this, oh man, what do they call that? There's a name for that. I want to say, is it test? I forget what it's called. I think it's called, is it the test qubit? Can anyone remember what it is? Control, that's it, the control. Yeah. Okay. You can see by inspection that it is a permutation, so it must be a unitary transformation. Yes. Interesting. That's a clever way to think about it. I didn't think about it that way.
It's in the name.
I know it's in the name, but they have other ones where it's like the same thing. You know, you're right. I know. I just forgot, okay? How can someone go through school and end up liking math? I love math. And I love physics. This is fun. I like math. I say that as a physicist. So I don't really mean math. Okay, anyways. So this is the matrix, and you can apply it to a qubit, and yeah, so if you apply it to the A, so this is the control. If A is 0, then it's going to just pass on through, and we'll get a 0, 0, so A and B will go through. If this comes through and this measures a 1, then it will flip the B qubit and change it into a different output than the input. Okay? Oh, man. Okay. What was that? Oh, it was a penny. Now, there's a couple of interesting things to talk about with the gates. Oh yeah, we have to talk about. Are we through that? Yeah, we're through that. Okay, so we have to talk about reversibility and invertibility. I don't know if that's a word. And the we're talking about reversibility and invertibility. And the real reason the XOR and X AND gates for the classical ones, and this is the part, this you guys all asked about it during the dry ice segments, And we were talking about XOR gates and XAND gates, and they don't exist in the quantum realm, right? The quantum realm. Why? Well, because they're not reversible. There's information lost in that situation, right? In an XOR gate. And I'll do the XOR gate specifically because, you know, that's one that's relevant. But if you have 2 bits, A and B, now these are classical bits, so you have 2 bits, A and B, and you have an output of 1, can you tell me what A bit was and what B bit was just based off the fact that you measured A1, right? And the idea is you cannot. There's no way for you to tell me what the A bit was and the B bit was just because you measured a 1 on the outset, right? And that's not so much, or I should say the output. This is not a measurement. Let me be a little bit more clear about this. In a classical bit, everything's measurements. But in a quantum computer, you can't have that type of quantum gate. Now, again, that could be a measurement gate, but not a quantum gate in this sense. Remember, I've been very, very specific that those are 2 different things, right? But you can't get the output in a quantum gate has to be unitary. You have to be able to reverse it and know what's on the inside and know the scheme of things. And it has to be unitary. You can't have any information lost as you're going about the thing. Now, again, like I said, once you take that measurement, you're going to have information lost. But like Admiral Entropy and I were talking about last week, that measurement does inherently, in fact, you know, collapse the wave function. You do lose information about from the inside. And that information on the inside is something that you're never, ever going to get. It's quantum information. It's not there, right? You can't ever access it. But you can utilize it throughout the inside of the gate, or inside of the circuit, okay? So it's a very interesting thing that happens, and it's the reason why you can't get any a gate that's exactly the same thing as an XOR or an XAND gate is because those are not reversible or invertible, okay? And there is another universality result that Nielsen and Chang mentioned that I want to make sure that I mention as well. Again, we're not going to talk about it until chapter 4 if we get that far. But it's a really interesting statement, and it's basically like you can construct any gate at all out of quantum gate, that is, not measurement again, out of a C0 gate and single qubit gates. So those are the single qubit gates we discussed and the C0 gate are the only things you need, and you can construct any type of quantum gate that follows unitarity and things like that. Let's see, what else is there? Let's see. Okay, so now we can talk about measurement gates. Let's talk about a property of measurement gates. Okay. Now remember, measurement gates. Okay, let me see. Hold on. Okay, so let me talk about measurement gates in a different sense. Okay. Measurement gates have this other property where you can actually measure things in different bases, right? Bradley, thank you for the follow. Just like you can have different bases in other quantum experiments, right? Like we could talk about the z basis and then describing an x basis and go back and forth and things like that. And it's the same thing with this. So let's define a different state. We'll call it a plus state. And it's going to be defined as 1 over the square root of 2. Again, we need that normalization. This one. Now this is going to look a little familiar when we do the -1. You guys are going to start to realize that these are simply just what? What gate specifically did we use to construct these? It's not there anymore. So you guys, I can actually ask you guys, and the answer is not on the board. But this looks very similar to something that we've done a lot of, or a specific gate that we established as being relevant. And we can rewrite the state psi. So if we have some state that's alpha 0 plus beta 1, now we can rewrite this in the following sense. Okay? We can write alpha times the plus state plus the minus state over the square root of 2 plus beta times the plus state minus the minus state all over the square root of 2. Okay? So if we just solve for the different states, oh, I have my chat going from my arm. So it's just the Hadamard Gate, right? It's the Hadamard Gate in disguise. That's really what this looks like, right? Just what it looks like. Okay? Come on. Okay. So then if we do this, we can actually rewrite it again as the following. If we have alpha plus beta divided by the square root of 2, we get the plus state. Oops. Have the plus state. And we can also write alpha minus beta divided by the square root of 2 and the minus state. And that's how we rewrite psi in a different basis, right? So now we can actually measure this in a different basis. We can measure for a plus or measure for a minus, as opposed to measuring for a 0 or a 1. And in it, we'll get a different probability amplitude. And there might be some certain situations where we can infer some stuff about those, namely the Stern-Gerlach. But again, we're not going to talk about that quite yet. That'll be later in this chapter, so it'll probably be like a week or 2 out. And we'll talk more about having a different basis for talking about the Stern-Gerlach again, because the Stern-Gerlach is kind of like a giant quantum computer, right? You have a quantum gate as the oven, the Stern-Gerlach oven, which is like a Hadamard gate, where it'll put in a superposition of two different states, and then it comes out, hits the magnetic field, and the magnetic field is like a measurement gate, where it actually collapses the wave function and snaps it into one of its positions, and then makes a measurement. I think it's important to emphasize that any unitary transformation can be realized with a 1-bit unitary transformation and the C naught, which is, I think, what you meant by any gate. Yes, yes. So what Hadamard entropy said is a better way of saying that you can construct any unitary transformation out of a 1-bit unitary gate and a C naught gate. You talking faster than a speeding bullet? I know, I'm a little amped up right now. Maybe the coffee. I gotta breathe. We're almost done. This is it. This is the last few sentences. This formalism, right? And that's what I said. It's useful in some sense. Like we can infer some stuff about the Stern-Gerlach experiment. But sometimes it's not the best because what do they say? Let me just read what they say. They say there are many reasons for using this extended formalisms for quantum measurements, but ultimately the best one is this. The formalism allows us to describe observed experimental results, as we will see them in our discussion of the Stern-Gerlach experiment. And even more sophisticated and convenient, but essentially equivalent formalism for describing quantum measurements is described in the next chapter. Yeah, we'll do that. But it's basically saying that it's difficult to make some of these measurements, but we can actually prescribe, based off of what we measure in experiments, a basis state, and then use this formalism to get the zeros and ones back out of it. Okay. I think that's it for today, guys. That's it. We learned about quantum gates. Next week we're going to talk about quantum. Like I said, if I stream next Friday, which is looking good, then we should be doing quantum circuits, and we'll actually start constructing some circuits and trying to follow along through. Bradley RL, if I did not say thank you and welcome, then thank you and welcome. Let's see here.